In this video, we're going to start looking at some battery technology that can be used not only in the appliance arena in cell phones and computers and whatnot, but also in vehicles in this era of electric vehicles. So by far the most common and exciting battery right now in mass production is the lithium-ion battery. There are several types of lithium-ion battery. I'm just going to show you a generic one. So generically, you could have lithium ions, the lithium ions could be charged or could discharge. You would charge to the anode, which, remember, if it's a battery, we're assuming a voltaic cell. If it's a voltaic cell, we assume that the anode is negatively charged, or discharged to the positively charged cathode. The example of this chemistry would be lithium 1 minus X, cobalt with 2 oxygens. So lithium 1 minus X, cobalt CO with 2 oxygens, solid. Lithium X, carbon 6, solid. So by no means do you have to memorize this chemistry. You'd be a chemistry nerd if you thought that you had to. And I love chemistry nerds as much as the next chemist. But you certainly don't have to. But try and understand eventually what's happening rather than worry about the details. 6 carbon solid and lithium COO2 solid. Okay, so this is pretty unusual chemistry, but let's dig into it. So in a fully charged cell, so if this is a fully recharged battery, so you've plugged your battery in overnight, X equals 1, and that would suggest a lithium-free COO2 cathode. So if fully charged, X is equal to 1. So 1 minus 1 is 0, so that would be gone. So the cathode is a lithium-free COO2. So essentially all of the lithium would be here. So eventually the lithium is going to transition over here. So there's going to be an exchange of lithium that way. During discharge of this battery, X heads towards 0. So it goes from a fully charged value of X close to 1, fully discharged close to 0. So during the discharge process, X goes from 1 to 0. And we know from our reduction potentials that the voltage is around 3.6 volts. Obviously it's positive because we have a battery, so therefore we have a galvanic cell or a voltaic cell. So we know that this means galvanic, voltaic. That's what's implied here by the word battery. Okay. To balance this charge, this proverbial flow of positive ions and positive lithium ions. So to balance this flow of positive lithium ions, then electrons would flow in the opposite direction. So positive lithium ions mechanically move in one direction, electrons mechanically move in the opposite direction to counter the charge. And obviously it's the movement of the electrons that we're interested in. Through an external circuit. So to balance this flow of lithium ions, positive lithium ions, electrons flow in the opposite direction through an external circuit. And this is obviously a redox process. When fully discharged, the cathode is lithium COO2. So the cathode goes from barren COO2 to lithium-laden COO2. And we can look at the oxidation state of cobalt. So the oxidation state of cobalt in the cathode is reduced from the +4 oxidation state to the +3 oxidation state. So let's have a look at that. So if we compare this species here, we're ignoring lithium because we assume that X is 1 when it's fully charged, so there is no lithium. So we know that just COO2 has a net charge of 0. We know that oxygen is in the -2 oxidation state, so therefore cobalt must be in the +4 oxidation state, because the +4 oxidation state plus 2 of the -2 oxidation states sum the oxidation state to 0. So we have a regular ionic compound. So we have a +4 oxidation state for cobalt when fully discharged. But when it's being chaperoned with lithium, then now we have the +1 oxidation state for lithium. So again, we're looking at the product now. And so if oxygen is still -2 oxidation state, essentially this has to be +3, because our two -2 oxidation state oxygens are quenched by the +4 oxidation state total of lithium and cobalt. So again, we've gone from the fully charged oxidation state of +4 for cobalt to the fully discharged oxidation state of +3 for cobalt in the product. So let's look at a type of question you could ask about lithium-ion batteries. And one of the reasons why I'm providing a question here, although typically my videos don't provide questions, I assume that the student's going to be looking at the assigned homework for questions. You don't find that many of this type of question in a textbook, so this is why I'm supplementing with a typical question here. So the question reads, a lithium-ion battery has a capacity of 3.4 watt-hours. This is a similar unit that your utility bill, typically in kilowatt-hours, but it's basically a way that you could quantify the power needed, where power is watt and hour is duration. So for what duration do you need this power for? If it operates at positive 3.6 volts, how many grams of lithium must migrate from the anode to the cathode to produce this capacity? Okay, so this would be a dimensional analysis problem where we're going to have ultimately grams of lithium ion as our target answer. So we would just naturally write gram of lithium ion here. By definition, if we look in our periodic table, the formula weight of lithium is 6.941 gram of lithium, and that's equal to a mole of lithium ion. we're not worried about the mass of the electron, it would be negligible here. So we're just taking the weight in grams of a mole's worth of lithium ion, and we would promote mole of lithium ion here, and we would cancel it thusly. I know that a mole of lithium ion is equivalent to 1 mole of electron. And I know that because lithium only has 1 valence electron, so under oxidation it would lose just 1 electron. Therefore, a mole of lithium ions would be equivalent to the loss of a mole's worth of electrons. So I can promote mole of electron up here. I know that a mole of electrons is equal to Faraday's number of charges, so 96485 Coulomb. So I could promote Coulomb up here. I know that a Coulomb, by definition, is an amp second. So a Coulomb is an amp second. This is actually a useful unit to recall. So let's write this here. 1 Coulomb is 1 amp second. That would be one I would try and remember moving forward. So I can promote amp second up here. And I'm actually going to promote amp first and then second later. But I'll just do them ahead of time here because I know I'm going to do them eventually. So I've got amp second here. Let's promote amp. I know that an amp volt is a watt. That's also a good one to know. So a watt of power is an amp volt. So I would also try and commit that to memory. So I've cancelled the amp already, but now I've got the second. Well, I know there's 3,600 seconds in an hour. So I've cancelled second. So if you look at the only units I have, I guess I need to add one more piece to this puzzle. I need to use my watt hour. Notice I have watt and hour as a denominator, so I can write watt hour as a numerator now. I've got my input power of 3.4 watt hour, and that's equal to 3.6 volts. So this was my raw input from the question, 3.4 watt hour at 3.6 volts. It came in here. Watt hour cancelled watt hour here. Voltage cancels voltage here. So if you look, there's no unit that survives anywhere other than gram of lithium. If you run this through, you get 0.24 grams of lithium ions. So for this capacity, you need to physically move 0.24 grams of lithium ion. In contrast to batteries, we have fuel cells. So we're going to introduce fuel cells here. And we'll not only introduce them, but we'll compare and contrast them with batteries. So let's start with batteries as a starting point. So batteries, and we've just finished looking at the lithium ion battery. Batteries are closed systems. So what we mean by closed is that there's no material exchange with the surrounding, there's only an energy exchange with the surrounding. So only energy is exchanged between I should have said between the system and the surrounding. So only energy is exchanged between the system and the surrounding. In contrast, fuel cells are open systems. so that energy and matter are exchanged between the system and the surroundings. So matter and energy is exchanged between the system and the surrounding. So this is the major difference between batteries and fuel cells. So the major difference between, for example, in the automotive industry, the electric vehicles that use batteries versus the hydrogen fuel cell cars that use hydrogen fuel cells. If we look at, for example, a hydrogen fuel cell car, which now are commercially available in 2020, we have oxidation at the anode, as you might expect from our two favorite Halloween costumes, an ox and a red cat. So an ox, we have an oxidation at the anode, and for a hydrogen fuel cell we would have hydrogen gas becoming two lots of proton. You can have proton or you can have hydronium, whichever you prefer, and two electrons. Okay, so hydrogen gas, two lots of H plus or two hydroniums, and two electrons. And by definition, E standard for this cell is 0 volts. So this would be the standard hydrogen cell, which everything else is measured based off of this, and we arbitrarily set this to 0. We would have reduction at the anode. So we've got our reduction at the cathode. We have our red cat. And for hydrogen fuel cell, we'd have oxygen gas and 4 hydronium. Actually, 4 hydronium and 4 electrons. To give 2 lots of water. And the E standard for this cell would be positive 1.229 volts. So combined together, remember that E standard is E standard cathode minus E standard anode, which would be the cathode value 1.229 volts minus the anode, which here is just 0 volts, which is plus 1.229 volts. Notice it's about, well, it's less than half of the potential, and I've just realized, I don't know how clear that was, it's less than half the potential of the lithium ion battery, but still enough potential that you could power something, you could power it enough to get a vehicle moving. So I've just tidied up the bottom of the board here and reiterated our 2 equations. So if we have this equation at the anode, so this is an oxidation at the anode, and this bottom equation is reduction at the cathode, then from our balancing redox equations in acidic and basic medium video, if we wanted to combine these two half equations, we would just have to scale the first half equation by a factor of 2. And we would do that because we have 4 electrons at the cathode. We also need 4 electrons at the anode because they're the same electrons. So we could rewrite this as 2 lots of hydrogen gas and oxygen gas and 4 hydronium and 4 electrons. So essentially combining all the reactants to give the products, we'd have 4 hydroniums and 4 electrons and 2 water. If we then go through and cancel any spectator ions, that's ions common to both sides. Initially, we get rid of electrons. You shouldn't have electrons in your final product. I've got 4 lots of hydronium on each side. So if I rewrote this, we can see that overall, the chemistry of a hydrogen fuel cell is just 2 lots of H2 gas and oxygen gas to give 2 lots of water. So essentially the only exhaust is water, so this is great for the environment. You can essentially just dribble water out the back of your vehicle, and water dribbling on a freeway or a road, a public road, to my knowledge is the only chemical that you have a right to dribble all over the road. So we're not breaking any laws by watering the road after us.